Okay, we're going to talk about the coagulation process. Okay, this I like to look at. There's two paths. And it looks like a Y. Okay, so you have the intrinsic pathway. And you have the extrinsic pathway. Okay, so let's talk about the intrinsic pathway first. Okay, with the intrinsic pathway, it's internal, so it's set off by you have collagen exposure. So you have a break in the body. Okay, so a break in the vessel wall. So you have a break in the vessel wall. So we have a break in the vessel wall. What this does is it stimulates platelets to go and stick to the site of injury. Platelets, adhesion to the walls. Hold on, let's make this a little bit better. So stimulates the platelets to adhere to the walls, okay? And upon arrival, these platelets release a bunch of things. So they release ADP, they release thrombin, they release thromboxane, A, and prostaglandin. What these do is they activate more platelets. To the site of injury. They also cause vasoconstriction, so that the smallest amount of fluid is going to get out. And it also stimulates the clotting cascade, which is what we're going to talk about. Okay, so it stimulates, you have many factors that are floating around in your blood, okay? They're inactivated. These factors are made by the liver, okay, randomly, and so they're put out by the liver, and they're just out there ready to be activated. With the intrinsic pathway, the first one that gets activated is 12. So it's going to get, 12 is going to get activated by this response right here, okay? So 12 gets activated, it becomes 12A, which we'll just call it 12A. It means it's activated. 12A then activates 11, factor 11. So factor 11 now becomes activated, okay? And activated 11 then activates factor 9. So 9 becomes activated, and then 9 activates 8, and 8 becomes activated. Okay? So it is a chain reaction. 12 gets activated, which then activates 11, which then activates 9, which then activates 8. Okay? Once 8 gets activated, it activates 10. Okay, so then 10 becomes activated, which then activates 5, which then activates 2. 2 is thrombin, by the way. So we'll put that here. And inactivated is prothrombin. Okay. And then this process is going to activate fibrinogen, which is factor 1. To become activated, which is, activated, to become fibrin. Okay, now these, the fibrin becomes fibrin strands, and it's these strands that create like a little net, along with factor 13, which, you know, you get a fibrin mesh. And this is going to trap cells and create a stable clot. Okay. And then later you have tissue plasminogen factor. So we're going to put this over here. That once that clot has served its purpose and we don't need it anymore, it will come and it will it'll break it up. Okay, so that's basically how our intrinsic pathway works. So that is, we are constantly injuring our internal body. I mean, even just day-to-day stuff, we have little nicks that happen on the inside of our vessels all the time, but we have this system in place so that we don't bleed out, right? So the other pathway we have is called the extrinsic pathway. Extrinsic, think of extrinsic as external. So it's an external injury. Okay, so you have an external injury. So activated by external injury. So that would be like a stabbing or bullet wound or whatever. It doesn't have to be that violent, but you know what I mean. So this stimulates this damage, so tissue damage. Is going to cause a release of tissue factor. Which is and thromboplastin. And tissue factor is 3. Factor 3. Okay, so we have an injury. So 3 gets activated. The activation of 3 causes an activation of 7. Activation of 7 then can cause activation of 10. Okay, so that's why you have intrinsic pathway, which is one side. You have extrinsic pathway, which is another side. And then you have a common pathway, because at 10, they're common. Okay, this is common. That means eventually both paths meet up. Okay? So now that we know the coagulation process, then we can talk about, okay, well, how do the different anticoagulants work? One thing I don't like is that it's called anticoagulants. It doesn't prevent coagulation. It just delays the coagulation. As we've seen, it is a chain reaction. When one gets activated, the next one, it activates the next one. And then once that one's activated, it activates the next one. So what anticoagulants do is that they bind or limit the supply of certain factors. So that when, say we have 12, well, we'll go ahead and talk about a real one. So we have heparin actually binds 9, okay, factor 9. So if we bind factor 9, okay, then that means activated 11 has a hard time finding 9, right? An available 9, a non-bound 9. So it delays the process from activated 11 to becoming activated 9, which was then going to activate 8, okay? So let's talk about that. Okay, so let's do a different color. We'll do red for Coumadin. Okay, so we have Coumadin, warfarin, okay? It actually binds vitamin K. So it is going to decrease factors that require vitamin K. So the liver can't make it. So it's going to decrease production of those factors, okay? Because the liver needs vitamin K in order to produce those, okay? So what are the factors that require vitamin K? Well, that would be 7 and 10 and 2. Okay, and 9, I believe, yep. And 9, okay? So what it's going to do, so the liver isn't going to be able to readily produce these factors because Coumadin is going to be limiting the amount of vitamin K that comes to the liver, okay, gets there. What's another one? Let's see, let's look at heparin. Make that one purple. So heparin. Heparin likes to bind 9. So let's go and put it that it binds 2A, 10, and 9. Oh gosh, well, let me do an A. There we go. Okay. So we've got 2 and 10 and 9. Okay. So you can notice right off the bat that heparin only works along the intrinsic pathway. So when we're doing lab work and we're trying to see how well is our intrinsic pathway working, we use a prothrombin. We use a activated partial thromboplastin time, which is a PTT, okay? So when we're measuring a PTT, we're measuring the intrinsic pathway. We're trying to figure out how long the time is in seconds to use that pathway, this one, the intrinsic pathway, okay? So with the other side, so the extrinsic pathway, we are checking, let me change if we want to see how well the extrinsic pathway is working, we'll use a PT time, prothrombin time, okay? to determine how that pathway, because the Coumadin works on the extrinsic, it works a little bit on the intrinsic as well. So, but we can use the PT to see, okay, how is it working? Okay. So when we want to know, so when a patient is on Coumadin, we are going to check PT times. And when a patient is on heparin, we're going to check PTT times. Okay? We're going to go in a little bit more detail later, but for now, this is what we need. We're going to talk about another one that we're going to be talking about, which is low molecular weight heparin. This is like enoxaparin, okay, which you guys give a lot of. This only acts on factor 10, okay? Okay. So because it only works on one factor, we don't have to do all the lab work that we have to do with heparin and Coumadin, because as you see, heparin and Coumadin work on many factors. So you never know, it works on so many that it can drastically increase or drastically decrease. Whereas with low molecular weight heparin or enoxaparin, it only works on one, so it can be very predictable. So we don't have to do lab work for that one. Okay, now we'll talk about in our notes, but that gives you a good overview of how the coagulation process works.